And now we have two reactants. Two reactants, NO and H2. And you see a coefficient for 2 here, hopefully the 1 here. And you're tempted to put a 2 here and a 1 here, which may or may not be true. It would be unusual if it does, because rarely do you get anything more than a second degree or second order reaction in a chemical reaction. But it is possible, so let's see if that is indeed the case. I would suspect this to be 1 and 1, but I really don't know. I haven't done the problem yet. We're going to do this together. So, we need to find both M and N. The last problem was kind of easy because we only had one variable. We didn't have to worry about another one. This is different because what's going to happen here is that we have to find a way to isolate one variable and just look at how that changes the rate without the other one changing. You know what I'm saying? It's like what we call a control in science. When you have a bunch of variables involved in a system and you're trying to make predictions about it, you want to isolate all the variables except, or you want to isolate one from all the other variables, get the other variables to not change while you change just one thing. Those others that are not changing, those are called controls. And then we looked at the one that does change. So that's what we need to look at here. We got 3 experiments that we've done here. And we want to find the concentration of NO when H2 is not changing. And we want to find the concentration of H2 when NO is not changing. That way we can see how the rate is affected by each one individually. We can put in our M and N, add the 2 together. That'll tell us the rate of, or the order of the reaction overall via each individual reaction, which is like what we did in the very beginning of this chapter. So let's start with the first, NO. We see that NO is changing from 1 to 2, and we see that H2 is not changing from 1 to 2. So this would be a good start here. So we go like this. Now, I really don't like that they put 12.8 times 10 to the negative 3. I know why they did it. Then they turn around and change it later on. I wish they had not done that, because you can see by looking at that that's double. They should not have done that, because that's not how you write scientific notation. You actually write it like this. And so to figure out how that changes, that, you know, you see that that's doubling, but it may not be so obvious when you see it that way. So you should take 1.28 times 10 to the negative 2, in this case 12.8 times 10 to the negative 3, divided by 6.4 times 10 to the negative 3. Either way that you do this, remember, it's the end of the arrow on top and the beginning of the arrow on bottom. When we divide this out, and yes indeed, this is 2. So you see that the concentration doubles. Now we want to see what happens to the rate when we do that. So we go in the same order that we changed here. So we're going to go from here to here. So that means then that we're going to have to take 1.0 times 10 to the negative 4 divided by 2.6 times 10 to the negative 5. This is not, now why they did it there and not do it there is beyond me. Probably because this isn't even clear if you did it that way. I mean, it's pretty obvious. And the thing you've got to remember, we're looking for whole numbers or very simple fractions, like 1/2 or negative 1 for an integer or 0. So your options really are 2, 1, 0, negative 1, and 1/2. Possibly negative 1/2, although I've never seen that. Anyway, when you do this, punch this out in the calculator. Take 1e negative 4 divided by 2.6 e negative 5. I get 3.85. Well, I know that can't possibly be the answer, because it's not a nice even whole number. So I'm going to change that to 4. Okay? So this is 4. Now 4 equals, now I put the m over here, and now I'm going to bring the whole thing over here, 2 to the m power, The value of m is indeed 2. 2 squared is 4. So m equals 2. So, yeah, it did work. In this case, it's the same thing. Alright, so Christmas is coming. I'm going to use a green pen with this and get a nice Christmassy look to this. Oh, joy to the world. Okay, so now we're going to change the H2, but not the NO. And the only way that the NO stays the same is from the first to the third. So we're going to go from the first to the third here. And so that means we're going to take 4.5 times 10 to the negative 3 over 2.2 times 10 to the negative 3. And we work that out. And we get 2.05. Again, that's a little bit ugly. We got to make it a whole number. So that means that this is going to be times 2 again. So it looks like it pretty much doubled. Now, since they had control of this, they could have changed it any way they want. Why they went from 2.2 to 4.5 is beyond me, but that's just an editorial comment. Come over here, and now we're looking at first and third. So we're going to go from here to here. Okay? So, that's going to be 5.1 times 10 to the negative 5th over 2.6 times 10 to the negative 5th. Divide that out. And again, 1.96. Round it off, that becomes 2. So 2 equals, now this is n power, because it's that exponent here. We'll take that, not the time sign, but that, put it right over here, 2 to the n power. And the value of n now becomes, of course, 1, because 2 to the first is 2. So the n just disappears, knowing that it is n implied 1. So now we have a third order reaction, something that is really, really rare. If this is indeed what we call an elementary reaction. I suspect that it's not, based upon that. Alright, so now we need to find the value of K. So let's rewrite this thing down. I'm using a nice pretty blue color. R equals K times the concentration, NO2, no, NO times NO squared times H2 to the first power. And again, you can pick any one of the three. You should get approximately the same value. He's slightly off because these aren't exactly double, so these get thrown off just a hair. I'll just go ahead and use number 1 here. The rate over there, the initial rate of this reaction is 2.6 times 10 to the negative 5. Oh, sorry, that's not the case, my bad. That's my rate. 2.6 times 10 to the negative 5, and that's multiple liter per second, equals, that's the second out of 5, K, which we don't know, like I tried to put that in, times NO squared. So NO, in the first one, is 6.4 times 10 to the negative 3. 6.4 times 10 to the negative 3 squared. And this is where people trip up, because a lot of the times you're only going to get 1 for an exponent. When you do enough problems, you start to quit looking to see what the exponent is, and then forget to bring it down, or just plain forget to bring it down, period, which is something I'm very capable of, as you'll probably see from time to time in this class. H2 here is 2.2 times 10 to the negative 3. Okay, now I'm not going to multiply that out. I'm going to let my calculator do all the work in one step. So to get K by itself, I'm going to divide both sides by 6.4 times 10 to the negative 3 squared, 2.2 times 10 to the negative 3. Here, oh, shoot, I've got my labels. So these are all moles per liter. That should be there, that should be there, that should be there, and that should be there. Nice. I just violated my own rule there. Good job, Aunt Vale. Alright, so now put 6.4 times 10 to the negative 3 moles per liter squared times 2.2 times 10 to the negative 3 moles per liter squared. Alright, so this cancels out completely. Leaves K. Okay, times 10. And then we'll go ahead and, oh wait, no, that's not square there. There's no square on that, so I gotta get rid of that square. Oh, some fly came on and I smashed it right there. That's just ugly. Okay, so 2.6e negative 5 divided by, and be careful on this, 6.4 e negative 3 squared. You can hit the square symbol. You don't have to worry about putting parentheses around it because the EE key puts imaginary parentheses around it. So you just go ahead and hit the square on that. And then since this is in the denominator with it, even though you're multiplying these two, you're actually dividing them both into this. So we hit the division sign again. 2.2, second E, negative 3, and there's no square. There's just some fly that I smashed. Hit enter, and I get round out the 3 sig figs, 289. Now, the label. Now remember, the last time we did it, we had s to the negative 1. Not so much this time. And I will use an opposite color so you can see this better. The mole per liter here, because there's only one, that's that stupid fly that I smashed. Moles per liter cancel out right there. And leave us just seconds here in the denominator. And here we got a square of the m as well as the square of the number. So that's going to be m squared in the denominator along with it. So the label for this is going to be 1 over meters squared times seconds. Now, again, you could write it like that, that's fine. I prefer the negative exponents. So I'm going to say that the answer for this is 289 moles per liter to the negative 2, s to the negative 1. Now, this is a third order reaction because 2 plus 1 equals 3. Third order. Now, the previous problem that we had was a first order reaction, and all we got was s to the negative 1. In this case, we've got m negative 2, s negative 1, and this is a third order reaction. I want you to notice the sum of the exponents of all of the m and s in this K label. This adds up to negative 3 when you add them up, and the other one's negative 1. It is exactly the same number as the order, only opposite sign. So you don't have to remember this because if you do all the algebra quickly, you shouldn't have to worry about it. But this should add up to negative 3 because it's third order. The other one adds up to negative 1 because it's first order. Keep that in mind when you do these problems. Alright, last problem we're going to do here. Just kidding on that whole last problem thing. I think we're just doing those too. Yes, we are. Okay, so you have 2 problems to do here. You'll be doing problem number 46, or 44 and 46. On page, I think 641. Yeah, page 641, 44, and 46.